Hello students, welcome to the today's session on trees and data structures. In today's session, myself along with Mr. Akshay will be explaining you to the fundamentals of the trees, and before that we will be speaking briefly about the data structures, why we need data structures, what are various data structures, and without them what are the problems we are going to face. And then we will be explaining about a particular data structure called trees and its variants like binary search trees, AVL trees, and how to insert, delete elements from those trees, and how to perform various operations, algorithms for implementing those operations, etc. So let me start today's session with the reason for having the data structures on the first hand. So please look at the slide. Why study data structures? Data structures is a tool for problem solving. The data should be structured in some way for writing efficient computer programs. The study of data structures and algorithms is fundamental to computer science and engineering. So using data structures, we can solve problems more easily rather than trying to solve any problem by writing a program without having knowledge of data structures. When you don't have knowledge of data structures, there is a chance that the data may be corrupted because you are using improper data structures which doesn't fit to your problem. So basically it is the problem which will be deciding on what data structures to be used, and ultimately it is the data structure which is going to make your program organization and program efficient and its execution in a simpler and a better manner. There were several data structures starting from arrays to AVL trees. But let me touch at different data structures before we go in depth on each of them. Some simple linear data structures are arrays, lists, stacks, and queues. Arrays is the most common way of representation, and basically lists, stacks, and queues can be represented using arrays or pointers. Whenever you are representing list, stack, or queue using array, we say that the representation is linear. When you are representing the same list, stack, and queue using pointers, we say that they are non-linear. So let me start with what are the advantages and disadvantages of each of them. Let me start with array. Array is the most common way in which the data is represented. Whenever we declare an array in the program, the number of elements that are inside an array are having memory locations reserved for them, usually in a sequential manner. So whenever I say that the size of an array is 10, then we say that the array can fit at most 10 elements, and 10 memory locations are reserved for this array inside the memory, and usually these 10 elements are put in a sequential manner. So what happens is, if the address of the first element in an array is 1, then we can easily say that the 10th element's address is 10. But at the same time, the operating system is having independence to perform several memory management techniques, due to which it might not be storing the elements of an array sequentially. But usually whenever you study arrays, you usually assume that the elements of an array are stored in a sequential manner. Then comes the list. List is a very common data structure which you see in your day-to-day life. Whenever you are traveling, you will be referring to the reservation lists, and whenever you are going to a directory, there you see a big list of entries in the directory wherein you have to search, And the next one comes is stack. Stack is something which you will be seeing in caves and other places where one will be taking plates one after another, and once they complete the work with that plate, they will be putting it. So always what happens is the last in will be the first out. So as long as you are taking, it will be 1, 2 like that, first one, second one, third one. But suppose that someone finish off the work with third one, they will be putting it, and that third will be the first one. So basically what we say is last in, first out. A stack will be representing a last in, first out feature in any system. Next comes queue. A queue is nothing but it is first in, first out. For example, you will be forming queue for several purposes like boarding a bus or taking something like a milk packets or anything else. What happens is if you are standing first, you will be served first. So first in, first out feature is supported by the queue. At the same time, the list, stack and queue can be implemented using an array or pointers. But whenever you are implementing them using an array, you are having some problems regarding inserting elements or deleting elements or even memory management, because you will have to perform a lot of operations to avail the memory that is occupied by that particular stack or queue in an efficient manner. Or else what happens is, though you are having a lot of memory free in a stack or queue, whenever I say a lot of free memory, it doesn't mean that your machine is having free memory. What I say is, when a stack is capable of holding 10 elements, and if it is holding only 6 or 7 elements, when you are representing it with an array, what happens is you will not be able to avail the remaining 4 places unless your algorithm is highly efficient. And even if it is efficient to avail that remaining places, you need to perform a lot of operations which are time consuming, and you cannot extend your stack beyond its capability of 10 elements. So there are several limitations with the implementation of stacks, queues and lists using arrays. When you try to implement the same with the pointers, then it will become easy for you to use them to their full capability. So let me just go through several advantages and disadvantages of these linear data structures when we implement them as we like, whether it is an array or pointer, depending on the problem you have in hand when you are writing a program. So array is the most common way of data representation. I request you to look at the slide. A list, in the case of a list, insertion in between is possible. The same is possible in the case of an array also, but the operations that you have to perform are too many and it is bit tedious. In the case of stack, it is very much useful in implementing procedure calls, particularly when you are using a recursion technique. Then comes queue. It simulates the first come first serve principle. So these are the simple linear data structures which we would like to bring to you. And why we need to study so many data structures? Basically the reason for that is different structures model different phenomena or application. For example, let us assume that we are writing a program which is dealing with the number of students in a class. Whenever you are speaking of a number of students in a class, the number is always fixed. Whenever something is fixed, you can go for an array because there is no need for you to extend. At most you will not be using all the locations, but definitely you will not be using more locations than what an array is having. And in the case of other things, like where you don't know the number exactly, let us say number of passengers in a bus, where the number of seats are fixed, but people who can board is more than that number. Nobody knows how many people can board it. So in such conditions, what happens is, when you declare an array of 50 and the number of passengers, when they exceed 50, you will be facing problem. The reason is your data structure cannot hold the details of more than 50 people. Under such circumstances, it will be wiser to look at some data structure which will be giving you scope to extend as the memory is available in your machine, so that there is no limit on the number of elements you can add or delete or hold, whatever it is. So an array is having a disadvantage of a limited memory. Though the machine is having memory, the array cannot extend itself as per the demand. So depending on the situation, we will be using different data structures. Since there are different models, we need to go through all these different data structures so that we can use them in our programs to model different situations and write programs accordingly. Let me bring some facts to your notice. Arrays are simple to create and use. Linear search is faster with arrays than linked lists. Insertions and deletions, particularly in the middle, are quite difficult to achieve with arrays. Linked lists are better equipped with handling insertions and deletions. So, let me concentrate on each of these facts. Arrays are simple to create and use. The reason for saying that arrays are simple to create and use is that you need to declare an array. More than that, there is nothing you have to do if you are going until the level of a procedural language like C language. If you are going to use arrays in in object-oriented programming languages, apart from just declaration, you need to initiate memory and other things. But speaking until C language, means I mean to say until procedure-oriented languages, the creation of an array is very simple, and it is always simple even in object-oriented programming languages when you compare it with the declaration of other data structures. Here you need to specify the data type of the elements. You need to specify the data type of the elements which are going to stay in the array. So let us say, suppose that you need to store 20 integers, then you will say that array of size 20 of type int. So that array can hold at most 20 integers. Suppose that you want to have 20 characters or 30 characters to be stored, then you will be declaring an array of 30 characters. So at most that array can hold 30 characters. So it's very simple. The first hand information you have to know is the number of elements that the array should hold and the data type of the elements that are to be stored inside that array. Now the second fact is that linear search is faster with arrays than linked lists. The reason for saying that linear search is always faster than with linked lists is, as I have already mentioned earlier, the elements of an array are stored sequentially to the extent possible. So what happens is, whenever suppose that you are storing 20 elements in an array, all the 20 are integers, and you are told that please search if there is number 6 in this array, and you can immediately search from the element 1 to the element 20, and whenever a matching occurs you can stop searching and say that it is found. It is simple because the number of swaps between the CPU and the memory are very less, because there is not much time consumed by the computer to resolve the addresses, because the address is always incremented by 1. If some element is at address 503, then the next element is at address 504 and then 505, so on. So there is no need for any formula to compute each and every address, except if you are going directly to some element without going to the between elements. So linear search is faster with arrays than linked lists. In the case of linked lists, it takes some time, because in a linked list what happens is the first element will be in one memory address, the second element need not be in some memory address which is immediate to the previous one. It can be anywhere. Let us say 503 is holding some element 10, the next element can be in the address 1000. So it's just simple, like when you are residing in houses one after another, it is easy to locate. Or else if we say that 20 people residing at different parts in Delhi and you have to find one person, it's very difficult and it takes a lot of time, and at each and every time you need to open the address and find out where it is and then go there and search. It is similar to the same. Whenever it is sequential, it is faster. Whenever it is not sequential, it consumes time. So we say that linear search is faster with arrays than linked lists. Let me go to the next point. Insertions and deletions, particularly in the middle, are quite difficult to achieve with arrays. The reason for this is, let us say 5 elements are placed in 5 memory locations one after another, and you need to insert some particular element in the position 3, but in position 3 you already have an element. So you need to move all the elements from that position by one position. So you need to move 3 elements and then insert this element. So what is happening is, if you have to put some element in position 3 in an array of 10 elements, you need to perform 7 operations, because you need to move all the elements from position 3 to position 10 by 1, and ultimately that position 10th element may get deleted because it doesn't have any place, because at most that array can hold 10 elements. So whenever you want to insert an element, you need to perform all these operations. So it is very time consuming and tedious. But at the same time, suppose that you are deleting an element, then you need to move the elements forward. Let us say you are deleting an element in the position 2. Then the element in the position 3 goes to the position 2, and so on. The position 10 goes to the position 9, and the position 10 should be made nil. So in this way, whenever you are deleting an element also, you need to perform almost the same number of operations, which is again tedious and time consuming. So the time complexity of your program increases whenever you are trying to perform insertion and deletion operations on the arrays. But at the same time, if you are trying to perform the same operations using a linked list, you are not going to have this problem of moving elements from one place to another to accommodate the new elements. The reason is, let us say 20 elements are scattered in memory at different memory locations, and you need to insert a particular element in some memory location to the third position. The only thing you will be doing is you will be updating your table with the address of that particular element to the position. Let us say you are putting it in the third position. Then the address of that particular element will be squeezed into that particular table, indicating the address. So what happens is, whenever you are traveling first, second, third, so the address is this one, you will be directly going. There is no need for you to disturb the addresses of the remaining elements. So without disturbing the addresses of remaining elements, you can always perform insertion and deletion operations in the linked lists. So insertion and deletion is always easier and efficient in linked lists rather than arrays. Let me go to the next point. The next point is, linked lists are better equipped with handling insertions and deletions, which I have just told you. But at the same time, you need to be a very good programmer to create in these linked lists and perform these insertion and deletion operations, because you will be using pointers rather than arrays in any particular programming language, and usually there will be a lot of memory errors whenever you are working with the pointers, because in the case of arrays the memory is fixed, there is no allocation or deallocation whenever you are working with arrays, because it is always allocated and it is not deallocated until you quit your program or particular procedure which declared the array. But in the case of linked lists, the program doesn't know at any point like how many maximum elements are going to be in that list, because whenever you want to have an element in the list, you will be allocating memory, and whenever you think that there is no need for that particular element, you will be deallocating it. So this particular disposing of will be creating problem, because some pointers will be hanging to some memory locations where you don't have any meaningful data. So always writing a program using pointers is bit difficult when compared to arrays, but that is the only efficient way of performing both insertion and deletion operations on elements. So now let us go to the question like, why we need trees at all. Previously we have seen why we need data structures, but let us now concentrate on why we need trees. All the linear structures are generally not suitable for representing hierarchical data. The hierarchical data has parent-children, superior-subordinate or similar relationships. A tree structure is a natural representation of hierarchy. Now let us go to the first point. All the linear structures are generally not suitable for representing hierarchical data. Whenever you think of hierarchical data, just think about the family tree. Your grandfathers, great-grandfathers and you. When you try to represent your entire ancestors and your family, it is nothing but it is a tree. Now how to represent this particular tree using a linear data structure which stores elements one after another? It's very difficult, because whenever you are trying to put one after another, again each element is having a similar structure. That's why we call it a hierarchical structure. And if at all you can accommodate this entire structure using arrays, which is possible with a very high difficulty of programming, then it is also very difficult to again make changes to this data, to add elements or insert, delete, to update the information. It's very difficult. So for this reason, we need a data structure called tree. The structure itself is hierarchical, and a tree will be used especially for storing hierarchical data. The hierarchical data has parent children, superior subordinate or similar relationships. And as I said, a tree structure is very natural to that of a family tree. Putting in view of all these hierarchical problems only, this tree data structure has been created. You will be encountering this particular data structure in a lot of operations in various subjects apart from this data structures paper, and even in real life when you are working on different software projects, you will be using this particular data structure very much frequently, and it's very essential for you to master the knowledge on trees as well as binary trees, binary search trees, height balance trees, B plus trees and B star trees, and you need to master all of them in order to become a very good programmer who will be using these trees efficiently and effectively for exploring solutions to various problems. Now let me concentrate on a programming technique called recursion. A recursion is a fundamental concept that is essential in the study of tree-based data structures. A general method of solving problems in which the problem under consideration is reduced to one or more simpler problems of similar nature but of smaller sizes. Recursion is nothing but it's a repetition of particular operation to a fewer number of elements, and you will be repeating that operation to the fewer and fewer, and ultimately you will be going to the least possible, and then you will be performing that operation backward. Let me just give an example. Suppose that you need to find the factorial of 5. Then what happens is the usual answer is 5 into 4 into 3 into 2 into 1. But then when you are trying to find out the factorial using the technique of recursion, you can say that 5 into factorial of 4. So now you have to compute the factorial of 4 and then multiply it with 5 to get the answer. Whenever you are thinking of factorial 4, it becomes 4 into 3 factorial. And whenever you try for factorial 3, it becomes 3 into factorial 2. So in this way, you will be solving a problem by solving different subproblems of it. This is called technique of recursion. Here what happens is you will be just performing the same operation on a fewer elements, and you will be doing it to the minimum possible, and then you will be expanding it from the backward. Now let me define a tree. A tree has a set of nodes, also called vertices, and a set of edges or branches such that there is a sequence of edges from any vertex to any other. There are no circuits, that is no paths starting from a vertex and returning to the same vertex. So the most important thing here is, in a tree you can travel from any vertex to another vertex. So a tree is always connected, means from any point you can travel to any other point. But at the same time, it doesn't mean that it is a circuit wherein you will be starting at one point and you will be reaching that point. So in a tree you will be having some root, and then you will be having different nodes, and one node is connected to another node directly or indirectly. Let me go through some basic properties of the trees. In computer applications, we need to study trees having one particular vertex singled out as the root, the rooted tree. In a rooted tree, there is still no way to tell left from right, or when one vertex has several children, to tell which is first, second, and so on. So in the ordered trees, we will be assigning an order to the children. So the most important 2 points about a tree is that it is always having one particular node as a root. Whenever we have a root, we say that the tree is a rooted tree. Then for this root you will be having children. But the only problem is you cannot identify particular child as the first child or second child or third child. Means there is no order for them. But if at all you can impose order on these children also, then we can call that tree as an ordered tree. Let me define a tree in a recursive manner. A tree is a finite non-empty set of elements containing a root, then subtrees having an order. This is a recursive definition of the tree. And to go for a more specialization of a particular tree, that is nothing but a binary tree. Though we will be studying trees, we will be concentrating 90% of our studies on the binary tree. A binary tree is a variant from tree having good number of differences between the both. You just cannot simplify a definition as a binary tree is a tree. The reason is a tree itself is having some features which a binary tree might not be having. The first point is a binary tree can be empty, but a tree cannot be empty. So there itself you have a difference. The definition of a binary tree is that it is a finite set of nodes that is either empty or root, left subtree and right subtree. The subtrees are themselves binary trees. Any subtree can be empty. So here the most important points are a binary tree can be empty. So I can say that a binary tree is having 0 number of nodes, that is possible. Then the important feature of a binary tree is that at most any node is having 2 children, not more than 2 children are there for any node. Only then we say that a tree is binary tree. Because suppose that you have one child, even then it qualifies to be called as a binary tree. But if it is having more than 2 children, we cannot say that it is a binary tree. And whenever we speak of subtrees, that is whenever you take a child of a node, assuming that particular child as the root, we can call all the nodes along with it under it as a subtree, and this subtree can be empty. So please look at the slide. This is an example binary tree. Please go through the configuration of this particular tree. In this example binary tree, the root is A, and then it is having 2 children B and C. So the entire binary tree's root is labeled as A, and it is having 2 children B and C. Then we can say that there are 2 subtrees here. One is with root as B and the other as with root as C. Again, when we concentrate on B, that B is a root with 2 children D and E, and here there are 2 subtrees again with roots D and E, and here you have to observe that D is not having any children. So D doesn't have any more subtrees and the children are nil for that. Then if you concentrate on E, there is one child for that which is G. So here you have one subtree for E, and for that subtree the root is G. So when you study this particular figure carefully, you will find that you have a root which is A, and then there are different children for different nodes, but never you have more than 2 children. If you have 2 children or less than that, only then it qualifies to be called as a binary tree. So this is one example for the binary tree. Now let us please have a look at that image. A complete binary tree. A complete binary tree means it satisfies all the requirements to be called as a binary tree, but it is having 2 children for each and every node. So though it can be called a binary tree with at most 2 children, in the case of complete binary tree, each and every node will be having 2 children except those of the bottom line, which are called leaf nodes. These leaf nodes doesn't have children, and that is the last level in the binary tree. So in a complete binary tree, you don't have any node without less than 2 children, and every node is having 2 children, at most leaf nodes. Such binary tree is called a complete binary tree. Now after discussing about the binary trees and trees, the most important question that will be hunting us is how to travel these trees, how to find out whether an element is there in the tree or not, how to find out whether a particular element is repeated, or how to delete an element from the tree. These issues come. To solve all these problems, we need to explore different ways of traveling through these trees. And before thinking of the algorithms that are used to travel these trees, there are some requirements that are to be followed by these algorithms. Let me just read through them. Each element or node is visited exactly once and needed for performing operations like display of tree, copying the tree, determining the height of tree. So to perform these operations, we need to travel a tree. So you just cannot display, copy or determine the height of the tree without traveling through all the elements of the tree. At the same time, you have different types of tree traversals. Let me go through each of them. The first one is in-order traversal. How to travel a binary tree using this particular in-order traversal. In in-order traversal, what happens is you will be first traveling through the left subtree, and then you will be visiting the root, and then you will be traveling the right subtree. So this is the order. First left subtree, so you keep on traveling to the left, and whenever there is no alternative to travel to the left, you print that particular element, and then you go to the root, and whenever there is no alternative to travel to the left, the point you visited last will become the root, and then go to the right and print the element until you can travel to the left from the node where you have gone by traveling to the right of your previous root. So just just have a look at this particular figure. The in-order traversal result for this particular image is DGBA HEICF. Let me explain how you got that one. The tree always starts at A, and you are traveling to the left possible, because in our in-order traversal we will be going to the left subtree first. So from A to B, and to the B the left child is D, but when you reach D there is no more left. So here you print that particular node, so you got D, and since this is the root of that particular subtree starting at D, now you have to go to the right subtree, because left subtree, root and right subtree is the pattern in which you travel. So when you travel to the right, it is G, but again there are no more children for that one to travel either left or right. So here you will be printing that particular element G, and after printing the G you will be going back G to D and then D to B. When you go to the B, to the left you can go, but then D you have already visited, and right there is no node, so you will be printing B. The same is the case, you will be visiting A, but when you visit A and print A, now you can travel to the right. So you have traveled one step to the right C, but your algorithm says that you have to travel to the left subtree, so you will be repeating it. So when you travel left, you go to E and then to H, and you print H there. So when you go back, you will be printing the root, which is nothing but E, and then you go to the right, you print I. Then you will be traveling back to the E, and from there the only alternative to travel is to the C, and you will be printing C, because you have to print the root before you go to the right subtree, and then you will be visiting the F, and ultimately you will be printing F. So you have visited all the nodes in the in-order traversal, and the pattern is D, G, B, A, H, E, I, C and F. This is the order in which you have traveled and you have printed the nodes. There are two more traversals, and let me go to the next traversal. Pre-order traversal. In this, you will be visiting the root first, and you will be printing it, and then you will be going to the left subtree, and you will be printing the root of that particular left subtree, and after traveling all the left subtrees from that particular left subtree, you will be concentrating on the right subtree. So let me explain the pattern of traveling for that particular tree. So you are starting at the root A and you print it, then you go to the left subtree B, and here again the root is B for this particular subtree from B, so you print B. Then you go to D, because that is the left subtree, again you print D. When you print D, you are not having any left subtree here, so you have to go to the right subtree. Right subtree is G, and after going to the right subtree G, the root is G for that particular right subtree, and after that to go to the left subtree you don't have any left subtree, and even you don't have the right subtree. So here you will be backtracking G to D, D to B and B to A, and from there again you will be going to the left subtree, but you don't have a left subtree. So go to the next tree, that is C, and travel to the left E. So you will be printing C, and then you will be printing E, which is root of the subtree, left subtree, and then H, which is root of the left subtree of E. And again go back, and now you will be printing I, which is right subtree of E, and then you will be printing F after traveling through C, because you have already traveled to the left of the E, and the only alternative is to travel to the right. So in this way, the order of the nodes visited in pre-order traversal is A, B, D, G, C, E, H, I, and F. Now the next and final traversal method is post-order traversal. In this, you will be first visiting the left subtree, print it, and then go to the right subtree, and then visit the root. So let us again start at A as usual, and now we will be going to the left subtree. So you are visiting to B to D. After going to the D, you don't have left subtree. So our algorithm says that you have to go to the right subtree. So the right subtree is nothing but it is G, and then here you don't have any left subtree or right subtree. So the next one is root. Root is nothing but G. So you will be printing G. After printing G, you go back, and here again the same situation. There is no left subtree, right subtree, you have already traveled. So print D. Now go to the B and A. So when you go to B, the same as the situation, you print B. But when you travel from B to A, here you have already traveled to the left subtree. Now you have to travel the right subtree. So you are going to the C, and then you go to the left subtree, go to the left subtree H, and since you don't have any alternative of traveling either left or right, you print the root, which is H. Then go back to the E. After you going back to the E, you have to go to the right, because you have already traveled left, and your algorithm says that you have to visit the right subtree after visiting the left subtree. So you print I, and after printing I, when you go back to the root, you will be printing the E. And after backtracking to the C, here you have already traveled to the left side. So the only right subtree available is with the root F, which you will be printing. And when you are going back, you will be visiting C, which you will be printing because it is the root of that particular subtree, and then you go back and print A. So the pattern of the travel is G, D, B, H, I, E, F, C, and A. So these are the most important tree traversals which are available on the binary trees, and you will be using one or the other to solve any of your problems. And you can implement these in order, post order, and pre-order traversals either using recursion or non-recursive methods, though using recursion technique is very much popular in implementing these traversals. Next comes is an expression tree, where you will be representing different expressions in the form of a binary tree. This is very much self-explanatory, but still I will be explaining you a bit. A plus B star C $A plus B star C. So here you are traveling to the A, and then you are printing plus, again you are going to B. It is nothing but it is in order traversal. You are traveling this particular tree in order, and when you travel it by in order traversal, you are getting the resultant expression. Just it's a test for you, and you take note down of this. You take note of this particular tree and try to arrive at that particular expression shown above. So here we have concentrated on pre-order, in-order, post-order traversals and expression trees, and prior to that I have introduced you to the data structures, for reasons for having data structures, and then introduction to the trees, reasons for having trees, and then binary trees, their introduction, and how to travel through these trees using in-order, pre-order and post-order traversals, and then ultimately going to the expression trees. And then you will be listening to Mr. Akshay about the binary search trees, height balance trees, the algorithms which will be used to implement them. So over to Akshay. Thank you very much.
Now let us talk about the binary search tree. What basically is the definition of binary search tree? Well, a binary search tree is, that is BST, is an ordered binary tree. You can look into the slide such that either it is an empty tree or each data value in its left subtree is less than the root value. That is one of the requirements, that whatever is falling to the left, that is less than the value or the key value which is available in the root, or each data value in its right subtree is greater than the root value. So these are the two basic properties. And finally, left and right subtrees are again binary search trees. So this particular property is contiguous. It goes on. It doesn't stop at this particular junction. I think we should look into the particular binary search tree so that this particular definition is more clear to us. Well, a sample binary search tree is there in your slide. What you can see over there is the root, right? So root, actually you have a value 5, and whatever is less than the root is into the left subtree. 3, it is less than root, so it is here. 2 is less than 3, so it is here, and 1 is less than 2, so it is falling onto the left side of the tree. Onto the right hand side, you can see somewhere you are having 5, 6, 6 is greater than 5, then you are having 9 over there, and 8 and 7 are falling towards the left of 9, right? Now please note, 8 and 7 are greater than 6 but less than 9, and that's why, since they are greater than 6, they are falling towards the right hand side of the 6, but since they are less than 9, they are falling towards the left hand side of this particular tree. So that is the basic objective as far as the recursive definition was concerned. That's what we wanted to say. The definition is recursive. It goes down deep to the level of leaf. The same principle should apply everywhere. Let us look into a tree which is not a binary search tree, and that will consolidate our definition. The tree given in this particular diagram, you see, you are having 3 less than 5, perfectly okay, but 2 is less than, no, 2 is less than 3. Over here, to the right of 3, the value which can be adjusted over here is 4. 6 cannot come here because 6 is more than 5, right? So anything which goes to the left has to be less than 5 first, and then it can come here. However, since 2 is less than 3, this particular leaf is a wrong leaf, and this is not a binary search tree. Similarly, over here, 7 and 8 are falling towards the right of 9, which is totally wrong. If at all they have to fall, then they can fall to the right of this particular place. If at all 2 has to fall, 2 can fall here, and 1 can further go down there in a binary search tree. So this is, in a nutshell, what we are trying to say, what a binary search tree is all about. But what are the operations which we can perform on these binary search trees? Well, some of the simple operations which you can perform on binary search trees are initialization of BST. Why initialization? Because we can always have an empty tree. Okay, so that initialization is going to make you, this operation makes an empty binary BST for you. Checks whether BST is empty. That operation is going to see, suppose you are trying to do a search operation, it is definitely going to check it. Suppose you want to insert an element, probably if there is an empty tree, then a root is to be created. Like that, these things are required for those. Create a node for BST. You create a node, that is, allocate memory space for a new node. So memory space is to be allocated, the key values are to be placed, and then that is, you will doing returns with error if no space is available, and thereafter, that is, first you create a node, and then certain links are to be created to the place where exactly this particular BST node is to be put. So creation is a separate operation. You create it, and later on you will be inserting it. Then you have searching for a node, searching for a particular place or particular key value in a particular binary search tree and finding whether something exists or not. Insert a node into BST, delete a node or subtree of a BST, update a node's data. Now this is a typical operation. If you want to update a node's data, that may change the location of that particular tree. So it tantamounts to say we might have to delete that particular node and reinsert it. Okay, there may be a possibility of that kind. Retrieve a node's data. If you want to retrieve some data from a node, that is what you got to do. And finally, you would like to traverse, which may be in order, pre-order or post-order in a binary search tree. So these are the common operations which you would like to have on a BST. But we would like to look into some of the basic operations out of these. And one of the very basic operation which I would like to see here is insertion into a BST. Now, if you want to insert an element into a BST, what are the steps? The first step will be to search the tree. So if you have written for searching, that step can directly be utilized here. But then algorithm should be jotted down for searching also. That is, what is the searching algorithm? Left is you compare with the root or the current node, and if the given data value you are searching is less than the key value available, you go to the left of the subtree, or you go to the left subtree, otherwise you go to the right subtree, and if the value is equal, you have found it, right? Second step which you will going through over here, if the key to be inserted is found in the tree, we do nothing, since duplicates are not allowed. Otherwise, a null pointer is reached. You will be reaching a null pointer, and that probably will be a leaf node, or it may be a node having whatever is the null pointer into. I mean that can have only maximum of one subtree. So other null you will be reaching. What you will be doing over there? Allocating the memory. That is, you will be creating the node and then adding pointer from the last point traversed. So that is the way you will be inserting an element into a binary search tree. How you will be deleting a node from this particular tree? Well, deleting operation is very, very simple. Search the BST for the node to be deleted. If found, if leaf, delete the parent pointer. The pointer which is coming from the parent, simply delete it. Free the memory used by this particular deleted node. If the node has one child, its parent pointer needs to be adjusted. If it has two child, then probably the whole node need to be adjusted. We would like to see these two insertion and deletion things with the help of an example. Now how do we do insertion and deletion? Suppose this was our original tree, and an element 5 is to be inserted. What is the value over here? 8. 5 is less than 8, so we are looking for, or we are searching the tree. So we traverse to the left, we find 6. 6 is more than the tree, right? So we traverse to the left. We find 5 is more than 1, so we further traverse on. And what we find here is 5 is still more than this particular value. So, and that particular, we reach a null pointer, and that is where we insert. We place this particular pointer, and simply from 4 to 5 we add a pointer to the right. That is right pointer of 4, we add the pointer to 4. So this is a way of insertion. Suppose I want to delete. Suppose I want to delete this particular element 5. What we really need to do, we'll start from here. We move here. First we got to search. We search 5 and we can simply delete it by simply removing the pointer from here. So removing the leaf is no problem. But suppose we wanted to remove 4. In that particular case, the simplest way first to search, and since 4 is having a right child, that right child will go to the right of 1. Suppose 4 was having a left child, that left child is also more than 1. So even that left child will go to the right of 1. So that is the way we can simply delete if we have one such child. But suppose we want to delete the root itself, then what is going to happen? For that, I think we would like to see to a better tree diagram where we are trying to delete the root. Suppose I want to delete the root. In that case, which is the most likely successor which can replace this particular value? Well, it is the rightmost child to the left subtree, because that will contain the maximum value, or the leftmost child to the right subtree, because that is going to contain the least value. What you can see over here, the leftmost child is 11, the rightmost child is 9. So what we got to do? We got to put this particular node value over there. In turn, we are trying to delete now node 9 from this particular case. And what we find, that means it becomes once again a recursive algorithm for deletion. And fortunately for us, in this particular case, we find that this particular node is having just one left child, and that will become the right child of 7, and that is the way you will delete this particular node. That is, 9 will go over here, 8 will come here, and this will be totally eliminated. That is the way you delete when you are looking into a situation where you have, or where you are trying to delete from the root. But one thing which we have noticed, in all these subtrees, over a period of time, a binary tree may deteriorate. It really depends on how you are inserting elements into a binary search tree. And suppose you insert 5, 4, 3, 2, 1, you will get a complete line, list kind of a binary search tree. And searching in list is very, very poor. After all, why do we need search trees? We are using search trees to improve search performance. That is definitely we want it to have. We would like to have some sort of binary order of search, or binary search kind of order of log n. But in addition, we also want to minimize the time of insertions and time of deletions. And if a binary tree deteriorates to a list, almost all the advantages which we were wanting to have are totally out, eliminated. So we need to have, for those situations, what we call height balanced trees. One of the height balanced trees is what we have, AVL tree. Now what we are having is, each node of an AVL tree has the property that the height of the left and right subtree is plus minus 1. So they can have one level more, or maximum, that is what you can have. And for that we define something called a balancing factor, which is defined as the height of left subtree minus height of the right subtree. So balancing factor. Now what are the possible values which this particular balance factor can have? Well, in an AVL tree, the balance factor which are recommended should be 0. That means the height of the left subtree is same as the height of right subtree, then only you will have 0. Plus 1, when the height of left subtree is 1 more than the height of right subtree, then you are going to have plus 1 as the value. And finally minus 1, when the height of left subtree is less by 1 to the height of right subtree. That is what you are going to get as the values for balancing factors. But what is the importance of these balancing factors? Well, these balancing factors will be utilized for insertions and maybe at the time of deletions. Would like to see how exactly these balancing factors influence the algorithm for insertion in an AVL tree. For that we have to look into an example of insertion into an AVL tree. let's look into the insertions. And what we want to insert in an AVL tree is some names instead of numbers, and they are to be inserted in their lexicographic fashion. That simply means we'll be inserting bin, fem, ind, ni and lal in this particular order. What we are seeing, bin is the lowest, fem is greater than bin, ind is still greater than bin, f is greater than fem, ni is greater than ind. However, lal is greater than ind because L is comes after I, but it is less than ni. And we would like to see how in AVL tree we would like to balance the insertions during the time of insertions itself. So let us look into the insertions as far as by this particular tree is concerned. So what will be the first step? We get bin and we create the root. Bin is the root in this particular case. What is the height of the left subtree? 0. What is the height of the right subtree? 0. Therefore, a balancing factor for this particular case is 0. Now we want to insert fem. Where exactly fem should go? Definitely to the right of it because it is more than bin. So we would like to insert it towards the right. What is the balancing factor at fem? 0. And what will be the balancing factor over here? Since what is the height of left subtree? 0. What is the right subtree height? 1. So over here it should be 0 minus 1, that is minus 1. Now we want to insert ind. Now what happens? Bin, fem. What is ind? It is more than bin, so we will go towards the right. It is still more than the fem, so we still go towards the right. Right? And what we find? The balancing factor over here is 0. Over here it is 0 minus 1, that is minus 1. But in this particular case, what is the balancing factor? Left subtree has a height 0 and right subtree has a height 1 and 2. That simply means the height or the balancing factor at this particular case is minus 2, and this is not allowed. So what do we do? If this is not allowed, we got to balance the thing out. How to do that? This is called rotation. What was the problem? The problem was to the right of this particular node, wherever there is a minus 2, to the right of it, okay, so that is RR, to the right of it, Similar analogy can be onto the LL side, and the rotation will be of the same type. What rotation we are going to have in this particular case? We will make the tree up from this particular place. So fem will become the root, bin the left, right, and ind the right, and this is what we will get as our rotation. Fem becomes the root, we have changed the root. Bin becomes the left subtree, and in becomes the right subtree. So this is a perfectly balanced tree. Now we want to insert NE. It can easily be added to the right of this particular place. Okay. However, why it can be added? Over here the balancing factor is minus 1. But what is the balancing factor over here? 1 minus 2, and that is minus 1. So it is perfectly okay. The difference is still within plus minus 1. But what happens when we want to insert lal? The balancing factor in this particular case is 0. It is to be added to the left of net. Over here it becomes plus 1. However, in this particular case it is minus 2, and it is even in this particular case it is minus 2, right? The nearest to the node you have inserted, that is the most concerned node to us. So this is the subtree we would like to do the balancing first, and this balancing should automatically balance out the other thing. Now this rotation is right, left, and this is called RL rotation. What do we do in RL rotation? The bottommost is taken over here. This becomes the left, and this remains the right of this, right? And this is what exactly we are going to do over here. That is, NEE becomes, Lal becomes the root of this particular subtree, IND is the left subtree, this is the right subtree, and you see because of that the overall tree is now also balanced. So these are the basic styles of rotations in any AVL trees. So with this we would like to end this particular session. In today's session we have discussed about the linear data structures, some of their properties, the trees, the binary search trees and AVL trees, a little bit of those insertions. I think with this you would be able to do some of the basic operations with the trees. With this, I think thanks for today. We will see you soon in the next session.